So last time, we were discussing the relationship between O3 and SO3, right? And we saw that SO3 was a non-abelian group, O3 as well, of course. And SO3 was the group of rotations, okay? Okay. And then we saw that SO3 has SO2 as a subgroup. And there are different ways of embedding SO3. We saw 3 such embeddings, right? The embedding of the SO2 as a subgroup of rotation in the XY plane, another in the YZ plane, another in the ZX plane. You can choose your own different 2 planes, and that'll give you a different embedding of SO2 within SO3. Okay, so, but SO2 by itself is an abelian group, right? And it's a group of rotation in 2D. Okay. Now, these are examples of continuous groups. And today I want to discuss about the one-dimensional continuous groups. And today I will also introduce the notion of a Lie group. Okay, so I'm going to make a very bold claim at the beginning and then justify it, although it's not going to be a proof, is that there are only 2 continuous groups in one dimension, up to isomorphisms. So up to isomorphisms, there are only 2 continuous groups with dimension 1. Okay? By dimension, I mean the number of independent parameters that we need to describe the group. Okay? So the number 1 is R1. Okay? What is R1? It's the set of all real numbers under addition. So one of the first peer assessment open response problem was to show that this is isomorphic. What was this isomorphic to? Can someone remind me?
Circle.
Not quite.
No, not a circle.
Complex number with 0i.
Complex number with 0i. Yeah, well, that's kind of a
plus 0i.
Sorry? No, I know what you mean, but that's kind of a that's not a trivial. That's a trivial isomorphism, right? You're just describing the real numbers. You're just saying that the real numbers is a subset of the complex numbers. Is there a continuous group, a one-dimensional continuous group under multiplication?
So I was wondering if we like leave the 0 alone, will it be like there can be a group, but I don't know if that will be an isomorphism from R to R addition to R multiplication.
Right. Is there a one-dimensional, is there a different one-dimensional, continuous group that we saw, which was not U1, which is not the circle?
Oh, SO2.
Yeah, SO2 is not isomorphic to R1. We'll see why. What about the positive real numbers that exclude 0 under multiplication? Is that a group?
Yeah.
Yes, sir.
So if A is in this, so is this, right? What is, and the identity element is just 1. So that this is also a group. And I'm claiming that R1 is R1 with the, with plus as the operation is isomorphic to R plus of 1 with multiplication. Can somebody tell me what the map is?
E to the x.
Exponential map.
Right. So the map is, we take an element in A and we map it to that. The inverse map is we take an element in B and take its log, right? So just showing that these two groups are isomorphic. Now, one of the things I want to notice is that R1 is a non-compact manifold. Okay, which means that its volume is it's infinite, right? Okay, so this is one of the groups that's possible in one dimension. The other one is U1. So U1 is the group of all phases of the form e to the power I theta under multiplication. Okay. So if I have e to the power theta 1 and I multiply it to e to the power theta 2, I get e to the power I theta 1 plus theta 2. Okay. Where the thetas take value within 0 to 2 pi.
So is it necessary to contain the theta in this region, or can we not just say it's a real number?
Yeah, then you would not have a unique parameterization of your group elements.
Oh, okay.
Yeah. Right. You would not have. So this means that the parameter space of U1 is a circle, right? Which is a compact manifold. So the topology of these two different continuous groups is different. Okay, although locally, they're essentially the same. You're just adding two real numbers. Okay, so these are the two groups in one dimension. Now I'm going to introduce another group in one dimension, which of course will be isomorphic to one of these groups, but which has very interesting physical applications. So it's although it's isomorphic to one of these groups, it's worth studying by itself. Okay, before we do that, do we have any questions?
Is the second set compact because theta goes from 0 to 2 pi?
Yeah.
Okay.
So SO2 is like isomorphic to U1 in some sense.
Sorry?
Is SO2 isomorphic to U1?
Exactly.
Yeah, because both are compact.
SO2 is isomorphic to U1. And the isomorphism is that if I have, say, cosine of theta minus sine of theta plus sine of theta.
That's the
cosine of-
matrix representation of complex numbers essentially, isn't it?
Yeah. So this goes to e to the power I theta. Okay. This is the isomorphism. And it's, of course, goes both ways. Very good, Naeem.